Okay, so today we will continue our conversation of path integrals in quantum mechanics, and we will introduce the we'll do set up the stage for perturbation theory. Most of what I say today you have seen in one way or another in your advanced quantum mechanics courses, but it's good to remind ourselves of the terminology, the role of these this mathematics, and because we're going to directly generalize it in quantum field theory, and it will be helpful to keep the continuity of it. And some of you guys might not have seen this discussion. So what we're going to do today is we're going to set up the basics of perturbation theories in quantum mechanics, which is 0 plus 1 dimensional QFT. And we're going to define the S matrix, and I will clarify exactly what I mean by this. As a matter of fact, actually, maybe it's a good point to comment. When we started the course, we said that one important advantage of quantum field theory is that it's a multi-particle theory, right, to start with. Now, problems such as scattering that we're going to be interested in defining, you could talk about scattering of n particles to m particles, right? And the way you set up the calculation in quantum mechanics will have in it n incoming particles and m outgoing particles. And whereas in quantum field theory, there's just one formalism that deals with it all. We also mentioned in quantum field theory, there is pair production. Particle number is not conserved. And that is crucial for scattering. Because if you send in a bunch of particles and particles could be created in the process, then you want your formulation to keep track of it in a systematic, organized way. And quantum field theory does that for you. All right, with those comments, I'll start with a review of our discussion from last time, and then we'll talk about perturbation theory and set up the stage for scattering. And in the next few lectures, what we're going to do is that we're going to take this path integral formalism and propagator and S matrix we have defined, generalize it to quantum field theory. And basically, we'll see the perturbation theory we're going to discuss today, called Born series, is going to evolve into something that becomes Feynman diagrams. All right. Stop me at any point if something is unclear. So let's recall what we discussed last time. We said that in lecture 16, we started with quantum mechanics. So we are in the Heisenberg picture. So there are operator observable Qi. Observable Q is a function. Well, actually, observable Q is a function of time. So at some initial time Ti, you could prepare a state Qi Ti, which is the eigenstate. It's like a ket x. It's the eigenstate of Q of Ti operator with eigenvalue Qi, right? This means that at time Ti in this state, the particle is sitting at a single point. The wave function corresponding to it is a Dirac delta. Is a Dirac delta. It's non-normalizable, so it's understood as a limit. And then we said that propagator is the overlap, which is otherwise known as the amplitude for the particle initially prepared in an exact energy eigenstate of the Q operator location at location Ti at location Qi to end up at time Tf at location Qf, right? So this is what the propagator is. It's a particular observable in quantum mechanics. It's not observable as in like a self-adjoint operator, but something you can observe in quantum mechanics, as in you could measure. All right. So that's what the propagator is. And then we said that we wanted to wrote down the propagator in terms of the phase space integral. So recall that if you're in 1 plus 1 dimensions, in 1 plus 1 dimensions, so Q is your position operator. The momentum is P, so your phase space is 2-dimensional. We wrote down this by inserting the resolution of identity inside, by taking time and split it into many, many pieces. and inserting resolutions of identity, and every step we wrote down the propagator in terms of a functional integral over all possible path histories in phase space, right? All possible Q of t's and P of t's. So and then there's a weight, which is an exponent. Is a phase, the exponent of which is just PQ dot minus the Hamiltonian. This is all in the phase space. The picture to have in mind is something like this. So at time ti, we split it into many, many pieces, and we inserted resolution of identity. Now I'm drawing this picture only for path in space, but what's actually happening is that the path integral is a path integral over the phase space. We said in the case that your Hamiltonian, this guy, is just p squared over 2m plus some v of q, which means that your interactions are only a function of location, space, and not momenta, then you could perform the momentum path integral, functional integral, this guy, explicitly, and then you end up with this picture I was advocating down here. So this picture becomes exact. And then the momentum integral, we could do it because it's just a Gaussian integral, or it's like a set of Gaussian integrals. The result is this thing. This delta t is the little time intervals. We split our tf minus ti into n pieces, and delta t is tf minus ti divided by n. So the teeny tiny infinitesimal time interval they want to take away. We said that there's a divergent quantity that sits here, right? That's a normalization. It needs to be regulated, and this is just intrinsically there. There are always such things. So a mathematician might say that path integral is ill-defined. That's because they're referring to this thing. But in physics, we always think about some sort of separation of scales, meaning that in the ultraviolet deep, very, very short time scales, the physics is going to be low energy, low frequency physics is independent of the UV physics, high frequency. So no matter how you regulate this, it shouldn't matter for your low energy observables, and we are just going to carry it along as a constant, even though it's formally infinite. But recall, I told you earlier in the context of quantum field theory, this means that every theory is effective. They're all defined with a natural cutoff, right? All right, so then we derive the principle of least action from these path integrals using the stationary phase approximation. Basically the saddle point of this action. So now after you do the path integral over the phase space, you have these, every path is the weight of every path in the path integral is just e to the power of I action corresponding to that path divided by h bar. So the stationary phase approximation tells you that this path integral is dominated by the saddle point to this phase. So you will have to vary s of q of t with respect to q of t, and to find it, you have to extremize it. And the result of the extremization is precisely what the least action principle is, that we just introduced it in lecture 2, 3, whatever it was. Here's the derivation of it from quantum mechanics. And what the regime in which the stationary approximation emerges is when the phase oscillates really, really rapidly. So that's the regime where h bar is tiny, right? That's the regime we think the classical physics will emerge. And the picture to have in mind is that all these different paths, they contribute, but their contribution basically, according to saddle point approximation, because they oscillate so rapidly, when they arrive at T of F, the actions basically destructively interfere, so they cancel out, except for basically the paths that are localized on the least action, on the extremization, extremizing path. All right. We said that the propagator is a green function for the Schrodinger operator. Schrodinger operator is precisely this beast, this object that we usually set, we act with this on the wave function, set it equal to 0. That's called the Schrodinger equation. but now you could act with this on the propagator, and then you realize that as the propagator is nothing but the propagator is nothing but the green function for the Schrodinger operator. We mentioned that in path integral formulation quantum mechanics as another formulation, we can deal with observables. The observables are there, and we naturally calculate the matrix elements of observables. So some q hat of t prime. Recall that we're always in the Schrodinger picture, so observables are dependent on time. The matrix element like this is calculated simply by inserting some q of t prime. This notation means that you're performing a path integral with initial and final condition for the path to be on qi to be q at point start at point qi at time ti and end on qf at time tf. Any questions about this part? All right. Then we said that path integrals naturally prepare for you time-ordered observables, meaning that if you just naively put in qt prime, qt double prime inside the path integral, that is not equal to this observable qt prime, qt double prime is equal to the time-ordered observable, right? So that is another thing that we mentioned. It's a homework problem that we're going to go through. But it's just like you just follow your nose, you take two conditions, two cases. T prime is larger than T double prime and vice versa, and the other way around, and you do the calculation and you find that the time order one is the one that pops out of the path integral. So path integrals are convenient for that because time ordering is important in quantum mechanics. Then we finally commented on quantum equations of motion, which is, well, what is the meaning? What if we said the classical equations of motion comes from the stationary wave approximation. So you could treat del S del Q as an operator in the path integral. So by the virtue, then you can learn that you can just, we said this, by change of variable inside the path integral, you can prove that all the matrix elements of this operator are zero. Well, not all the matrix elements, but these matrix elements of this operator are zero. But if you stick in any operator O next to it, then using the path integral, basically integration by parts, you can show that this is equivalent to the derivative or del Q acting on observable O. So that's a quick summary of what we went over in the last lecture. Today, we're going to continue our discussion of path integrals, discussing perturbation theory for the propagator K, and then we're going to also define S matrix. And today will be the last part of this discussion in quantum mechanics. As of next lecture, we'll start generalizing this to quantum field theory. This is mostly just to make sure we're all on the same page in our advanced quantum mechanics background. Any questions? Thoughts, concerns? All right. So perturbation theory. Let's recall what perturbation theory, what is the perturbation theory we're interested in, that we're going to discuss. Let me start with the case of a simple problem, which is scattering of two particles. This is the kind of problem that we might be interested in quantum field theory or quantum mechanics. So you have two particles. This is a space-time diagram. They interact at some point, and then they go away. Now, in quantum mechanics, if you want to set up this calculation, we say that there is a potential between the two. It's only a function of their distance because of translation invariance of assuming translation invariance. So we have to set up the time-dependent Schrodinger equation, right? So there is a wave function of the two particles. They could be distinguishable, indistinguishable, blah, 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 fermionic, bosonic. You have to calculate IH bar del T of it is basically the free part of the Schrodinger equation plus the interaction. but now it's a time-dependent setup, so the interaction depends on the positions, and positions depend on time. So you will have to solve this time-dependent Schrodinger equation. Well, this is too difficult. The short answer is this is too difficult, except for super special cases, although I'm lying a little bit. I'm not real. I shouldn't be setting this problem in 1 plus 1. I should be setting up in higher dimensions. 1 plus 1 is very special. We don't worry about that for now. That's why I put these vectors up here. So this is too difficult. So we have to use approximations in quantum mechanics. One approximation is an approximation in which one of these particles, or this could be a M to N particle, M to M particle scattering. You could view the whole calculation from the point of view of a single particle. So from the point of view of the single particle basically feels an effective potential due to the presence of all the other ones. So to justify this regime, one way to think about it is, imagine one of the particles is very heavy, so its Q is barely moving under the interaction with the other one. So we can view it as some sort of a fixed potential that's preparing because its position is not changing. And this other particle is interacting with that potential. This is some sort of a semi-classical approximation, right? So the problem simplifies. There's a Q, there's a V of Q. Like, for example, there's a heavy atom sitting somewhere and some charged particle is just coming and flying around and moves around in the potential of this heavy atom. Hydrogen atom is such an approximation, right? The nucleus is very, very heavy, and you just solve for the electrons that rotate or spin around the nucleus. All right, so this approximation, to think about it as a single particle scattering off of a potential. There's an ingoing wave, so you send a wave coming in from infinity, and then it scatters off and goes back. So I'm just setting up the stage. There could be some transition amplitude, things can go through, blah, blah, blah. This is a classic scattering problem in quantum mechanics, right? So I'm just drawing it schematically. There's some sort of potential, you send some wave from infinity, it comes, interacts with this potential, is deflected, ends up somewhere else, and there's an outgoing wave. Good? Any questions? So for the remainder of this lecture, we're going to be working in this approximation, unless I specifically mention. We're going to be working in this approximation where there is a fixed potential and your particle is interacting with it. It's a semi-classical limit. All right. I just said words to justify it. There is a way of rigorously going through justifying it, but anyway. So now next, so far I've used approximations, but that approximation has had to do with bringing down an n particle problem, turning an n particle problem to one single particle problem, right? But it's still, from the point of view of single particle quantum mechanics, is an exact problem. There's an exact Schrodinger equation you have to solve. Here's where perturbation theory comes in. So we're going to assume small interactions, or small between the two particles, or small potential in a sense. So in what sense do I mean that? In the following sense, if I look at the propagator, recall the propagator was something like this, right? So there was a path integral, e to the power of I s q over h bar. In the action, we're going to split s to, there will be a term which is s naught, and then there will be an interaction term, s of I, right? I'm going to assume s of I is much smaller than s0. So to be more specific, let's just talk in terms of the potential. So this is my propagator. So it should be d dq e to the power of minus s naught over h bar minus I over h bar, the integral of ti to tf dt vqt, right? Now, I'm going to assume this whole thing in the exponent is small. Recall exponents always have to be dimensionless. So when you say something is small, you are talking in terms of dimensionless parameters. So it means that the total amount of action due to interaction, which is this term, integral of VQT from Ti to Tf, has to be much smaller than h bar. H bar had units, right? So in units of h bar has to be small. What are the units of h bar? Does anyone know? It's the units of action as well.
Angular
Joule
momentum.
seconds.
Yeah, well, what other quantity in physics has
Angular momentum.
angular momentum? Lovely, thank you. Yeah, so it's basically units of angular momentum. That's the approximation we're dealing with, right? So now, of course, what you can do is I could take this exponent, you could take this exponent and expand it because you assume that the exponent is small. So you're going to get, you get 1 minus 1 over h bar integral of Ti to Tf dt VQT plus higher order terms. Is the nature of the expansion clear? It's kind of a crazy assumption. It's a very, very weak interaction assumption. You should barely interact. You barely interact, right? Okay, so now after we do expand this, we recognize the 0th order term as K0. This is we call it as K0 is propagator for the free theory. So we're going to spend quite a bit of time working out the propagator in the free theory using path integrals. Then we're going to look at the first order approximation. Okay, but the picture I want you guys to have in this perturbation theory is this. It's the regime in which there are free particles. The interaction is so weak that the propagator is like a free particle propagating, some interaction happening at some point, then freely propagating, some other interaction happening, and freely propagating and some other interaction happening, right? So for example, this 4 interactions is order 4. This is a lot less likely. So it's a regime which physically can think of as like a large mean free path. There's a particle that freely propagates and barely interacts, right? So the first order approximation is then you just you interact with the potential just once. Good. These are the diagrams that are going to turn into Feynman diagrams, but at the moment we're not discussing Feynman law. We're discussing scattering off of a potential in quantum mechanics. Any questions? Any questions about this part? So next, to tell you where I'm going to discuss the K0 term, the free propagator, and then we're going to come back to K1. Good. So the free propagator. So the free propagator is, you could calculate it explicitly. Why? Because the action is Q dot squared for the free theory, and that's just Gaussian. So you could do it explicitly, right? The same way that we calculate that we perform the path integral over momentum space explicitly because it was Gaussian. So again, the same way that we did the path integral over momenta, we're gonna do it over space as well for the free theory. We're gonna need to regulate it, of course, because we said that these path integrals have these divergences. So we first split Tf minus Ti to n parts. We call that T delta n. And then we introduce this vector, which is, it's an n vector. It has the location. It's a history of the particle at all these different points as it goes along, right? It's a particular path. It's a discretized path, right? Q1, Q2 to Qn minus 1. Is it clear? It's just a path of the particle. So it's a particular this is Q0, this is Q1, this is Q2, this is Q3, this is QF, QI, right? All right, so now what we have to do is we're gonna do the path integral over space, but because we had Q dot squared, we'll have to do Qj plus 1 minus Qj squared. That's time derivative, right? because we have discretized time. That's this our discretized derivative is going to be difference of qj plus 1 minus qj, right? So that's what we have to calculate. This calculation even looks very, very close to calculation of section lecture 2 when we're talking about we're talking about particles on lattice modeled by a bunch of springs attaching them. If you look at this action, you could write it, because we introduced this vector, you could write it as Q transpose M, some matrix Q. And the matrix is something like this, right? It just follows from the calculation. You could, in the matrix language or vector language, you realize that you could introduce this A vector, which is basically Q initial, Q final, and you repackage your whole action in the following form. So Q transpose, these are matrix multiplications, right? And your matrix is just not diagonal, right? Again, similar to the first, the example of springs, what we have to do is that we have to find the normal modes. We do this by shifting the change of variable that shifts the variable q to q prime. And now after some algebra that you're going to work out in the homework, it's going to look, your action is going to look like this: q prime transpose mq prime, and then this constant that comes out, which is only a function of qf and qi. Now it's just a Gaussian integral we can do, right? It basically becomes the following Gaussian integral. You have to take the limit of n going to infinity of e to the power of minus, so that you take this factor out, right? I've introduced a parameter sigma for convenience. You're going to go through this in your homework, but there will be these parameters that are delta. So sigma has 1 over delta t in it. That's the only thing that you need to know. When delta t becomes 0, this thing is blowing up, and also there's a power of n to it, right? So that's also another source of it whether or not it blows up is something that you have to take to play with the orders. Okay, so you have to perform a path integral over all these q's. These are Gaussian integrals. You could do it. You will do it in your homework. And this is the final answer that you get. Final answer that you get. Now, I want to make a bunch of comments about this. One thing that comes out of this path integral is a step function of tf minus ti. The path integral makes sure that final time is larger than initial time. This means, in our language of quantum field theory, if you recall, this means a retarded propagator. There's a delta function explicitly in there. This is a parameter. This is a coefficient, coefficient that is just 1 over tf minus ti to some power, right? And then there is a Gaussian phase. That is the result of the retarded propagator. The thing to keep track of is the Gaussian phase, the exponent up here, and this step function. If you repeat the calculation in d dimensions, and scatter off of a potential that's like spherically symmetric. Well, actually, sorry, we're not scattering off yet quite. You're looking at the free propagator in d dimensions. If you do that, d spatial dimension, you'll learn that this half is replaced by d over 2, and this qf minus qi squared is replaced by the norm of the vector qf minus the norm of vector qi. No other changes happen. This answer, this retarded propagator, I want to comment again, I've said this before, but it's the green function for the free Schrodinger operator. All right? Any questions about this calculation of the free propagator? So there's a step function in there. It's a retarded propagator. It's something that has 1 over tf minus ti to some power d over 2, right? It's good to think about the structure of it. And then it has an exponential phase that is telling you that tells you about the width of the wave function, the width of the propagator, how it propagates. If you are familiar with heat kernels, this is really like intimately tied to heat kernels, because basically the Schrodinger equation you're trying to solve is the heat equation with an I somewhere in there. That is this I. We're basically solving the heat equation with an I. Any questions? All right. Now, the form of the propagator as is a little bit complicated and not necessarily the most convenient. If you recall, the reason is simply that in real space, the Schrodinger equation is a differential operator. But if you recall the way that we went around this and all the examples we've looked at, from the springs attaching atoms to now, the trick is always Fourier transform. So we Fourier transform to simplify to turn our differential equations into algebraic equations, right? So what we're going to do is we're going to Fourier transform and go to spatial momentum space. To go to spatial momentum space, so the Fourier transform of a Q of F is going to be P of F. These are spatial vectors, momenta, and Q of I is P of I. Whoops. Sorry. I do not want to say that. That's wrong. Okay. Good. All right. So what we have to do is here's your for your propagator, free propagator. We have to Fourier transform it, and I've just put out explicitly the step function outside, right? It's just for convenience. You plug in the expression that I found here, right? Inside this, you have to do this Fourier transform. This guy appears with a minus sign and no minus sign here because they have T of F minus. Sorry, it's because of the fact that one of them is ket, the other one is bra. So to do this integral, you already know that the Fourier transform of a Gaussian is a Gaussian, right? So you should expect to get a Gaussian at the end. Now, we usually introduce these, to decouple these modes, we introduce these quote-unquote center of mass coordinates. These are not center of mass in a sense, but we basically add and subtract the final initial Q and final initial momenta such that we could write down these phases, right, in this elegant form. The average momenta, the sum of the momenta, is Fourier variable to the difference of spatial locations and vice versa. So now you have to do two integrals. One of them is over the sum or average of positions. The other one is at the difference of positions, right? The one that's over the sum will give a delta function. Delta function over what? Delta function over the sum of the final and the difference of the final and initial momentum. Does that have a name in physics? It's called conservation of momentum. A delta function of delta of P of F minus P of I appearing in any calculation, quantum mechanics or physics, means conservation of momentum. Initial momenta have to be equal to final momenta. That just comes from the fact that after you introduce these average and subtractive variables, the integral over the added variable is just a simple phase, Fourier transform a simple phase, which is a Dirac delta function. That's your momentum conservation, right? Then the other integral is a little bit trickier, but it's still a Gaussian. You do the integral, it's not all that complicated. It's a Gaussian integral. You do it by completing the square. The final answer is going to look like this. 2 pi h bar to the power of d D-dimensional, D is space dimension, okay? Momentum conservation is, of course, there. This little variable P is P of F minus P of I, right? So it's the total momentum, the creation of momentum, conservation momentum in a sense, right? Then you obtain this step function, which makes sure that final time is before, is after initial time, right? So it's retarded propagator. And then, as we'd expected, the Fourier transform of a Gaussian is going to be a Gaussian. T of F minus T of I multiplied by the sum of the momenta, right? Now, an interesting thing that you observe here is that the propagator, if you recall this, I just want to draw an analogy. Remember that I said that propagator is an analogy between quantum mechanics and field theory. Propagator is like the 2-point function. And here we're looking at, so it's 0 plus 1 dimensional. So your 2-point functions are only separated in time. If you recall, I said that we calculated the 2-point function in free field theory. And then we said, because of Lorentz invariance, you could always make them to be separated only in time. And the result was oscillating, right? In some sort of a small mass regime. It was just a phase that was oscillating with frequency that was set by the mass of the particle. Here, what we're finding is that it's an oscillating phase, and the frequency is set by p squared over 2m. Because the theory is non-relativistic, that is the dispersion that is imposed on us by the assumptions of the theory, right? So the propagator is going to be an oscillation with frequency set by p squared over 2m energy. Good? Is this clear? If you recall in that calculation of the 2-point function, what we did next was we Fourier transform in P0. Sorry, in time. And then we took the P0, right, which is the Fourier variable to time. P0 has a name, it's energy, right? And then we talked about analytically continuing in P0, analytically continuing in time, in energy. That's what we're going to do next in the context of quantum mechanics, right? So what we're going to do next is Fourier transform in time. The Fourier variable conjugate to Ti is going to, I'm going to call it EI, initial energy. Fourier variable to final time, I'm going to call it E of F, right? So here's my Fourier transform variable. The function, I'll just have to integrate over Ti, Tf with these two phases. Again, there's a sign difference between the two because one of them initial and final have to do with Ket and Bra. All right, so we plug in the expression that we had before. We have the momentum conservation. We have to do this integral, right? Now we notice that the fact that we had a retarded function comes in, right? So we define this variable tau, which is time difference, because of time translation invariance, we can get rid of, well, we just work with Ti and the tau. We repackage the integral as an integral over initial Ti and an integral over tau. We notice that the integral over tau is ill-behaved. It's a phase that's oscillating forever from time t0 until in eternity. This was the same issue that we encountered in the 2-point function. Our integration path was going through a pole. The way we deal with it is we dealt with it was deforming the contour in the P0 plane. P0 is energy, giving energy a tiny bit of complex variable. We do this exact same thing here. We introduce a tiny epsilon parameter, I epsilon, and that will make sure that phase will make sure that this integral will converge. This is a trick that we use in physics complex analysis all the time. If your domain, if your integral goes through a, well, I'm not gonna teach mathematical physics now. So yeah, the answer is going to be, after you do the integral and keeping track of that small I epsilon, is going to look like this. So let me just comment again. This is conservation of momentum. We knew it before. There is an energy conservation that pops out. E of f has to be, there's a Dirac delta function of E of f and E of E. And then you obtain the propagator in Fourier space, momentum and energy. It's IH bar, EF minus P squared over T2M plus I epsilon. Now, as I said, this I epsilon is similar to the Feynman propagator that we defined, right? There's one difference though. In the Feynman propagator, we had two poles, right? Here we have a single pole. It has to do with the fact that in this problem we're solving is non-relativistic. So there is a particle, but no antiparticle. In the problem we were solving earlier, there was a pair of particle-antiparticle, right? And they both appear as two poles in the integral, right? Here, there's only one solution. So the classical dispersion relation, which is when EF is PF squared over 2M, right? It's called the unshell condition. And it appears as the pole of the propagator. So let's just summarize the physics that we're learning. We took the propagator. The propagator is a function of initial space and time and final space and time. We knew that because of translation and time symmetries in time translations and space translations, we could get rid of some of these variables. So the translation, so let's say we're in 3 + 1 dimensions. So we have Q of I is 3 variables and T of I is 4th. And you have Q of F and T of F, which is 8, right? So because of translation in space and time, you can get rid of 4 variables. You could shift them. You could make Qi and Ti as you wish, set them to 0. In the Fourier space, those would correspond to momentum and energy conservation. Not surprisingly, we said that Noether currents, Noether charges, well, we said that every symmetry in quantum mechanics will have a consequence. If it's a continuous symmetry, will have a consequence that's a conservation law, right? That's the manifestation of that. So our remaining 4 variables, one of them is energy, the other one is momentum differences, right? Energy, yeah. No, maybe I shouldn't call it energy and momentum. There are 4 variables remaining, right? So, what do they want to say? Oh yeah, now you Fourier transform in those 4 variables, right? You go into momenta and energies, right? So you look at the propagator in the momentum space and energy space. The propagator in momentum and energy space, after these Fourier transform, the propagator was the green functions for Schrodinger operator. After this Fourier transform, Schrodinger operator, the Schrodinger, that equation, that green function equation is an algebraic equation. And what it looks like is 1 over a function that we're going to call dispersion relation plus I epsilon. So I said all of this to say that the propagator in Fourier space has poles that tell you about the particles of the theory. That's the lesson. If somebody comes to you and says, I have some sort of a funky theory that produces these propagators, you want to know what are the particles that are propagating this theory, you take that propagator, you Fourier transform, and you go to momentum and energy space. It better satisfy energy and momentum conservation. That knocks off a bunch of variables. The remaining piece will be basically 1 over something. The 0 of that something, the 0 of the denominator of the propagator, which is the poles of the propagator, are going to be telling you about where the particles are. If you find a pair with the energy flipped, that's a particle-antiparticle. If you only find 1, you're supposedly dealing with one of these non-relativistic regimes. All right? That's a very general lesson in field theory quantum mechanics. Any questions?
Yeah, I had a quick question. So like in like classic quantum scattering theory from like, graduate quantum mechanics, we have the time-independent Green's function of the Schrödinger equation. And we have like the poles on the real line that correspond to like bound and scattering states. But if you analytically continue the Green's function, you can find complex poles that correspond to pseudo-bound states. So can you do a similar thing here? And would that be like short-lived particles or something? Or
Okay, so there are a few comments. Poles that are on real momenta have to do with on-shell conditions for particles. Poles that are off of the real axis, there are resonances. That's all I'm going to say. So there is a well-developed scattering theory and which deals with resonances, the physics of resonances, what they are, and the physics of particles, excitations, right? But let's leave it at that because your question is very loaded. There's a huge theory like developed for this. But any textbook you pick on scattering theory will have a long extended discussion of this, even at the level of quantum mechanics. Any other questions? There's actually an approach to quantum field theory based on the so-called analyticity, which assumes that if I give you the correlators, or let's say the propagator, or the S matrix, we're going to be having to find the S matrix, and I tell you where the poles are in the complex plane, you assuming analyticity elsewhere, you could reconstruct that theory using analytic continuation. This is the so-called S matrix program as a non-perturbative approach or definition of quantum field theory. It's a semi-successful program. Let's just leave it at that. All right, any other questions? So I don't know how comfortable you guys are with green functions. So I'm just gonna discuss them a little bit in more detail. They are super intuitive. They are very, very valuable as a way for building intuition. So I said this actually already. I said that in relativistic free scalar field, we saw that the propagator has two poles, which were the zeros of this p mu plus m squared minus I epsilon. The unshell condition is where when this vanishes, when it's not zero, we call that an off-shell propagator. Another name for it is a virtual particle. So when people talk about a virtual particle, what they mean is an off-shell propagator. Good. That's the only meaning that you could associate to a virtual particle. There are no virtual particles. Particles correspond to poles of the propagator in the momentum space. When it's off-shell, then you call it a virtual particle. All right, so green functions. So what is the story of green functions? Green functions are basically matrix inversions for differential equations. Let's say you have a matrix equation. Some matrix L of ML times some matrix K gives you identity, right? I've written it, repeated indices are summed over, right? This is matrix multiplication. L times K is identity. So what is K? Is L minus 1. Good? Very good. So what if your matrix index was continuous? Then the expression you find, Kronecker delta becomes a Dirac delta. A matrix becomes a bilinear, and your sum matrix multiplication becomes an integral over the second variable. This is matrix multiplication. This is exactly this equation, right? For a case where if your index variable, the label of your matrix was continuous. Good. Now, differential equations you could treat them exactly the same way. You have a differential, so this L of x and mu, take it to be some L of x, some delta of x mu. For example, L of X mu, you could take it to be only a function of the difference, right? And you could take it to be all sorts of derivative function. This L of X could be a whole bunch of derivatives. What am I trying to say here? If you have a differential equation and you discretize it, it becomes matrix multiplication. To solve this equation, you just have to invert a matrix. If you have when you find green functions, what you are finding is you're first discretizing your differential equation. Your green equation is basically some matrix multiplied by some other matrix is equal to identity. You'll have to invert that and treat the variables as continuous. As usual, Fourier transform is the way to go. So you Fourier transform this k of x minus y and L of x minus y. So that in Fourier space, you literally have L of k of k is equal to 1. Let's work out an example. Take this L of x mu operator I was talking about to be the Schrodinger operator. After you Fourier transform it, in the energy and momentum space, it becomes E minus k squared over 2m. So you have E minus k squared over 2m times k of k is equal to 1. To find the green functions, you just divide 1 by this. What did we find? You found your propagator, right? It's just 1 over the Fourier transform of the differential equation, your equations of motion. That's it. There's no magic to it. It's a very intuitive way of thinking about stuff, right? So you might, if you're wondering why is the dispersion relation showing up in the denominator of the propagator? It's just because by definition, propagator is 1 over the equations of motion. That's the very definition of it. Good? Any questions? Again, Fourier transform is the key idea is Fourier transform. The reason we do Fourier transform is that Fourier transform will turn our differential equations into algebraic equations, and then inversion is just obvious. Good? All right. Any questions? All right. So this wraps up our discussion of case 0. We started by defining perturbation theory, and we calculated the free propagator so far. That's all we've done. We discovered energy conservation. We discovered momentum conservation. And then the remainder was an oscillating phase with a frequency that was on shell. In the Fourier space, energy and momentum, we found that this is 1 or IH bar over the dispersion relation. Right? The poles of the propagator, we interpret them as particles on the real p-axis. Those are the zeros of the plot. Yeah. All right, so now let's move on to the first order term. What is the first order term? Well, if you recall, we have this Q. Let's first actually it was basically an insertion of integral of d of t. It was I over h bar, integral of d of t, ti to tf, v of q t, right? That's what the term was inside the path integral. So here is your the way we're going to deal with it. We're going to take the integral over dt and discretize it. So this is the discretization. The rest is going to be the path integral. I'm going to do the path. Is this clear, or should I write down? So this was the expression. D of qi equal to, sorry. Let me just write it this way. Qi ti, qf tf, right? E to the power of I s naught of q over h bar, integral of ti tf I h bar or minus I h bar, d of t, v of q, and t, right? This was our K1. So what I'm gonna do is that I'm gonna take this integral and discretize it, put it inside the path integral, and now it's just a bunch of moments of a Gaussian integral. Okay, so this is that integral over t, and these are the integrals that have to do with discretization on my path integral, the free path integral. And then this is also the free propagator bit, the free part. All right, so what does it look like? There's dqj, because you're integrating over all possible qj's, and then tj, you discretize this. This is the expression you have. What you do is you split up the sigma to the power of n squared into two parts. One of them, you put it into j over 2 and n minus j over 2. You split up your integrals also for the number 1 to number j, and then j onward to n. The net result, the reason you do this is to repackage this as minus ih bar, integral of ti to tf dt that you already had, integral over dq vqt, with the propagators on both sides. I'll give you a physical picture for this very quickly. Thanks to Feynman, we know exactly what picture to draw. But this is algebra so far, but you notice that because inside each of these propagators, one thing that's super nice about this is that inside each of these propagators, there are these step functions, which will ensure you could just relax these integrals above and below. You could just relax them and integrate from minus infinity to infinity. These are things that you will go through in your homework. And then finally, you find K1 as the following integral. Minus I over h bar, integral from minus infinity to infinity dq, free propagator v free propagator. So what does that mean? Means that your particle is propagating free with k naught. An interaction happens at position q and time t. That is your v. Then the rest of the time it propagates for k0. This was your ti, this is your tf. This is the cartoon picture to have. Now, because it can occur at any time q, any position q, and any time t, you integrate over all q's and all t's. But in this approximation, only one interaction happens only once, but we don't know where, so we integrate over all possible places where the interaction can happen. All right, so this looks super messy. Well, if you repeat but in pictures, these Feynman type diagrams, it simplifies. If you did the same thing, this was the calculation for K1. If you did this for nth order, you're going to find the following expression: minus I over h bar to the power of n integrals in time, n integrals over q, an expression that looks like this. So previously, what we found was K0, V K0. At nth order, we're gonna find K0, V K0, V K0 all the way. So this is called Born series. Your propagator, your particle propagates freely with K0. Then here it interacts, gives V, then it propagates, then interacts, propagates, interacts. If it interacts n times, it's going to contribute to Kn. Because we don't know where these interactions happen, we integrate over all possible locations and times where n interactions can happen. Is that clear? These path integrals might look ugly, but these diagrams actually simplify them, right? So it is telling you what is actually going on, right? Well, in this approximation, this cartoon approximation, it's not true that the interaction is happening in a particular time, but you organize your perturbation theory in this language. This is the core idea behind Feynman diagrams, actually. Feynman diagrams are the generalization of this to quantum field theory. You have these integrals, you split them into pieces, and then you interpret them as some particle propagating free, some interaction happening, right? So the Feynman diagram is like a particle moving along. All of a sudden, some photon is emitted, then the particle freely propagates along. Something else happens. I don't know. Another thing is, right? And you're integrating over all possible ways that this can happen. Except that it's not in space or time. It's some sort of a virtual thing. Good? Any questions? This is Born approximate. This is Born series. It appears in scattering theory, in quantum mechanics, and perturbation theory. And QFT, finally, they're going to do direct generalizations of this. That's why I'm going over this. I don't know if you've seen this in advanced quantum mechanics, but it's a must. I think every graduate student should see this in advanced quantum mechanics. All right, now we get to finally S matrix. What is an S matrix? Let me give you some broad idea. S matrix is some sort of simple simple observables of quantum field theory or quantum mechanics. Quantum mechanics is 0 plus 1 dimensional quantum field theory, in which we've made an assumption that the interaction at far past is turned off, and in the far future is going to turn off again. This is a key assumption that underlies scattering theory. This should not be too exotic. In physics, we do assume this in physics and in space all the time. We always assume our functions, our fields, to not fluctuate wildly far away at infinity. We always want to set some sort of regularity condition really, really far away because we want to focus on physics here. This is S matrix is some sort of that turned around in time. Now it's a little bit more dramatic because in space we think correlations fall in distance, right? Clustering, but in time it's not quite true because things can oscillate forever. But physically, the idea of S matrix is that we adiabatically turn off the approximation and turn it on and turn it back off. Roughly speaking, it's something like this. Two particles are coming from long time ago, or a bunch of particles were really, really far from each other. Then they come all close and they interact and then they go away. When they were really, really far, the interaction was never zero. But we assume it was so tiny that we could have neglected that time at that time. When they come close to each other, then they can interact. And then when they go far away, we could neglect it again. So what is this business? We want to view it as an overlap of the incoming and outgoing particles. When I say at minus infinity in time, the interaction was turned off, it's a free theory. What I can do canonical quantization of that free theory. I end up with a Fock space. I can create particles at minus infinity in time. That Hilbert space, that Fock space, that free field theory is called the in Hilbert space. There's a vacuum, we call that vacuum in. There's a creation annihilation operator, we're going to call them creation annihilation in for creating in particles. In the far future, far eternity, like future eternity, t going to plus infinity, we also assume that interaction turns off, so there will be a new Fock space we're going to call Fock space out, creation annihilation operator and excited states of that Fock space. Now, S matrix says take some wave function of Fock space in. It had a single particle in it, two particles, who cares? Some wave function in the Fock space of n. Evolve it with the Hamiltonian of the interacting theory all the way until eternity, and then compare it with the Fock states of the Fock space out. That's what S matrix is. So particles that were free at long time ago. What does it mean to say 4 to 4 scattering? What is the meaning of 4? It means meaning of 4 particles is only a meaningful statement if you have absolutely no interactions. So the 4 to 4, that first 4 means that at minus infinity in time, when the interaction was turned off, you prepared a wave function psi of n, which is a wave function of 4 in particles in the Fock space in, on top of vacuum space, vac in, using creation in, annihilation in. Then you evolve this initial state in time for a very, very long time. And then you look at the overlap of that with out states. Because from the point of view of the observer at infinity plus infinity, what a free particle is does not match what the free particle is in the minus infinity. That's what a S matrices. Is it clear? Are there any questions? Questions? Sorry, I cannot hear this. All right.
How do you take the inner product if they live in different Fock spaces?
Well, I evolve it.
Oh,
That's the point.
okay.
Otherwise, I'll have a problem, right? I evolve it towards the future. And now, after I do this evolution, it will hopefully be in the final Hilbert space. What you're pointing out is that I didn't prove to you that the in state after e to the power of minus IHT, t large, will become a regular state of the final state, Hilbert space. As a matter of fact, that's an assumption we make in quantum field theory all the time, and we know that's a flawed assumption in the presence of massless particles. So that's a long story, very, very long story of infrared divergences. We're not going to be dealing with that for now. We're doing quantum field theory 1. So at this level, this assumption is fair and fine, and it holds in many theories of interest,
Thank you.
particular massive theories. Yeah.
Okay.
So finally, okay, I'm running out of time. Okay, so this is finally, I want to talk about the S matrix in quantum mechanics. Before talking about quantum field theory, I'm going to talk about S matrix in quantum mechanics for a single particle in the approximation when you scatter off of a potential. There's an S matrix, right? And I can use Born approximation to calculate the S matrix, right? How do I do that? Well, the effect of this guy is basically captured by the propagator. So if I want to calculate, so I take my psi n and I want to evolve it by e to the power of IH minus IH TF minus TI, right? What I have to do is that I take my psi n, I integrate it against the free propagator. Free or not free, actually interacting propagator. But in the expansion of the propagator, the first term is free, right? And then I get the psi plus q of ft of f. Psi plus q of ft of f is psi n evolved for a very, very long time. There is a term that is free, and then the first order term is q0 v q0. Good? In Born approximation, the first term was v, the q k0 v k0. Sorry, k0 free propagator interaction free propagator. And then if I want to calculate the S matrix, I'll have to take the overlap of this guy with some psi star out of q of ft of f. That's what the S matrix is. So it's a very helpful exercise to calculate, to do this. If you take the K0 part, which is a free propagator, put it in there and integrate, you're going to find that all that remains is momentum conservation, energy conservation. That's it. You're going to end up with momentum and energy conservation at the 0th order, which means that if your theory is free, minus infinity in time, the Hilbert space, the Fock space is the same thing as the Fock space of Fock, plus infinity in time, same Fock space, right? That's it. And the propagator does a bunch of phases. Like as particles propagate, things, there will be phases on shell phases. That's it. So that bit is boring, but it's important because it ensures energy conservation, energy and momentum conservation. Then the first order term is minus IH bar, integrals over Q's, right? So Qi and Q of F is about psi in and psi out, but there's one integral over Q of Q and T, which is about where the interaction happens, right? Because V is a function of Q and T. So there are two propagators. This is the propagator before the interaction happens. This is the propagator after the interaction happens, free propagators, right? And then there's psi out. This looks like an ugly expression, but that's why Feynman invented Feynman diagrams to keep track of this perturbation theory for the S matrix in a systematic way, right? So the point of this exercise was to first we defined S matrix and we saw how the perturbation theory of the propagator could be used for perturbation theory of the S matrix, right? Calculate S matrix perturbatively as Born series, order by order in interaction. All right, any questions? Okay, if there are no questions, let me just summarize and repeat the key parts. Today, we set up a perturbation theory. And for the propagator, I want to repeat the formal regime we worked in. It's a regime where the total amount of action due to interaction is much smaller than h bar. Sounds like an insanely small regime, small coupling regime. Then we took the propagator and expanded it, and we ended up with this picture. And these pictures represent integrals, right? Many integrals, path integrals and insertion of free propagators, blah, 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 right? But part of the exercise is to be able to get to a point where you stare at one of these diagrams and you can write down the integral. These diagrams are representing particular integrals, the same as Feynman diagrams. Feynman diagrams are going to be a bunch of shorthand notation, short form notation for some integrals, right? We commented on the free propagator, how the poles of it has to do with the poles of the real poles of propagator have to do with free particles, with particles of the theory. And then, yeah, I think that's all we said. And then we defined the S matrix and said that the S matrix, the perturbation theory of the propagator, will give you a perturbation theory systematically for the S matrix as a Born series. Any questions? All right. So this is the end of our discussion for path integrals in quantum mechanics. Starting next lecture, I'll start with a few other comments about the perturbation theory because I didn't have time to squeeze in this lecture. But after that, next lecture, basically, we're gonna start talking about QFT again, and we're gonna do path integrals in quantum field theory and calculate S matrices in quantum field theory, setting up this perturbation theory. Because as I said, calculating S matrices exactly is hopeless. And that story is called Feynman diagrams. That's the Feynman perturbation theory in quantum field theory. Any last questions? If not, thanks so much, guys. I'll post the homework tonight.
Thank you.
Bye.